Let's see, next up we have Chayawan Jaikla, who's a PhD student in geological sciences, who'll be talking about reconstruction of missing seismic data using a deep learning-based approach.
Thank you for the introduction, and good afternoon, everyone. Again, my name is Chayawan Jaikla, and I'm a PhD candidate in geological science at Stanford University. Today, I'm presenting my internship work at Shell on the reconstruction of missing seismic data using deep learning-based approach, and my collaborators of this project are Pandu Divrakota, Enkin Alkan, and Christian Sutton. Here is the slide for definition and cautionary notes. So Janaki introduced a little bit about seismic data, but let's go a little bit more detail about introduction of seismic data and its importance. So seismic data is the most common geophysical methodology used for oil and gas exploration and production. It provides a picture of subsurface, and here is the figure showing an example what the seismic data looks like. We can see lines representing different rocks formations because the seismic reflections occurs at boundaries of rocks with different physical properties. So what geoscientists do is they use seismic data to interpret structural and static information for reservoir, such as lateral extension of the reservoir, thickness of the reservoir, fault, and porosity. Here is some example of the interpreted seismic data from this raw seismic data. So in this picture, it's the interpretation helps geoscientists to determine the reservoir targets. So therefore, accurate and high-resolution seismic imaging play an important role in hydrocarbon exploration and production. However, the seismic data often come in partially missing data. So even we do any processes that Janaki mentioned in the previous talk, the data often come missing data. So we have to resolve this issue before going on to the next process. So in this study, we propose a deep learning-based approach to reconstruct missing seismic data. So this happened due to the limitation of data acquisition, economic limitations, and environmental constraints. The seismic data often have missing traces in the near offsets location. The current challenges are that conventional reconstruction and interpolation techniques are computationally expensive and require extensive parameterizations. We estimate the processing cost for one data set to be approximately $100,000, and it takes approximately 2 to 4 weeks to finish processing one data set. So another with the conventional approach is that it's often produce suboptimal and inconsistent results. So with these challenges, we propose an alternative approach by using a deep learning model to accurately reconstruct missing seismic data. Here, again, an example of the missing seismic data. On the x-axis is the offsets or horizontal distance between source and receivers. And the y-axis is the time, or how long does it take for the receiver to receive the seismic signals. The y-axis essentially represent the depth from the surface at the top. So the missing data are these vertical lines in the near offset zone. Our objective for this project is to develop a deep learning model which reconstruct missing seismic data in the blind field data set in order to use it in the exploration imaging workflow instead of the conventional approach. Here are some examples of the conventional approaches that I mentioned earlier that are computationally expensive and time-consuming. An example of conventional approach are Kirchhoff migration, and the current interpolation method is wave equation-based or rank reduction-based algorithms. There are attempts to use machine learning and deep learning-based approach to reconstruct missing seismic data. And here are some previous studies found in the literature. The models that have been used are support vector regression, custom design neural networks architectures such as UNet and ResNet, as well as GANs. These previous studies train and test the models by using synthetic data sets, which might not be applicable in the real-world data because real-world data is more noisy, it's more complicated than the synthetic data. So in this study, we use the real field data set to train test our model. And we chose to investigate UNet architecture to train and the reconstruction model, as UNet has been successfully applied in multiple applications in the field of computer vision. Here is the UNet architecture that we used. So UNet is the convolutional neural network that was developed for biomedical image segmentation, and it has been applied for image segmentation in different fields. The UNet architecture comprises encoder and decoder, and the differences of the UNet to the conventional auto-encoder is that the output size is equal to the input size, which is what we wanted for our purpose. To train the model, we use seismic images with some missing data as an input, and the output of the model is the complete seismic data set. So now let's look at how we prepare the dataset for training. Here is an example of the raw data of the seismic data. So due to the nature of the seismic data that has highest energy in the shallowest section of the image. So as you can see here, the shallow part has the higher signals than the deeper part. So we decided to slice the raw data set into 128 by 128 panels and rescale them into -1 and 1 in order to capture the signature of seismic data at all depth. So here is the results of the panels that we rescale and slicing from the original image. And this is another examples of training images that we slice from the deeper section of the original seismic data. So as a result of this rescaling and slicing, we have 7,000 images to train our model. So after getting scale image for training purposes, we carefully manipulated the data set to generate several scenarios of the input images in order to generate realistic training and testing data. We use original data as the ground truth for training. And we remove 3, 5, 8 seismic traces, or as you can see, the white vertical lines, removing this data set to represent the real world missing seismic data. Again, the white streak line here, yes, the missing seismic data set. We also investigate different loss function in this study, including mean square error, mean square absolute error, structural similarity index, and a combination of mean square error and structural similarity index. We evaluated our model performance to reconstruct an entire seismic images by using signal to noise ratio, or SNR. It is a ratio of the useful signal to the total noise component, and it is a common metric used in seismic data. So the higher values of SNRs indicate the better of the model. In addition to different loss function that we're experimenting, we also compare two ways of calculating loss function. The first approach is to calculate loss function by using an entire image. And the second approach is to only calculate the loss function only on the right half of the image where missing data exists. And this is the result on the test set. The y-axis here showing the average signal to noise ratio, or SNR, and the x-axis represent images from different depths of the original seismic image. The shallower depths is on the left and the deeper ones are to the right. The red curve are the results from case 1, calculating the loss function by using entire image. The average SNR ranges from 23 to 33, and the more missing traces, the lower average as SNR, which is expecting. These results are equivalent or better than the previous studies that trained the model with the synthetic dataset that are usually not as complex as the real-world dataset that we are using. And all the loss function that we try use similar SNR results. The blue curve here are the results from case 2, calculating the loss function by using only the right half of the image where missing data is. Similar to the scenarios, average SNR increase as we increase the number of missing data. But one thing to note is that calculating loss function by using entire image yields better results than only using the right half of image where the missing data exists. We suspect that this happened because the UNet architecture recreates the entire image and not just the missing data. So it is important to include the entire image in the loss function. Here are some examples of the prediction on the test set. The first image is the ground truth. The second is the input where we remove seismic traces in the near offset zones, as you can see in white streak lines here. The third image here is the model prediction, and the last image is the residue, which is calculated from subtracting the prediction from the ground truth. Another example from the deeper depth showing, again, ground truth, input, prediction, and residue. We observe that the residue almost contain nothing, which suggests that the prediction is similar to the ground truth. In addition, we can see that the prediction yield continuous lines. So as you can see here, one example, the red lines here, these are showing the continuous rise as a result of the model prediction, which sometimes we cannot achieve this result using conventional approaches. We also apply the trained model on a completely different data set that was acquired from different continent. Again, we showing the ground truth, the input, a model prediction, and residue in 3 different cases: the shallow area, the medium area, and the deeper area. The SNR values of this prediction are in the range of 15 to 20, which is acceptable considering that we applied a model on completely new data set that the model hasn't seen before. But there are definitely room for improvements before deploying this model. So in conclusion, our UNet model trained on real seismic dataset can achieve SNR values as high as the models in the literature that are trained and tested on synthetic datasets. This indicates that UNet architecture can be trained and applied for reconstruction of real seismic data that are generally more complex than synthetic dataset. One important thing is that the model can predict continuous seismic events in the near offset zone, which is an issue that hasn't been addressed before for the conventional approach. In addition, different loss functions that we experiment, which include mean square error, structural similarity index, and a combination of mean square error and structural similarity index, yield similar signals to noise ratio in the test set. And lastly, the UNet model trained on one dataset can be applied to another dataset. And this is very important conclusion for this study because the trained model will be significantly reduced cost and time to reconstruct missing seismic data from weeks to hours. Thank you for your attention, and I'll be happy to answer any questions.
That was great, thank you. I have one quick question while we wait for the chat. So the organizers who are collecting this data are probably going to ask, how little data can you get away with collecting and still be able to recover pretty much what you had in the original? It seemed like the 3, 5, and 8 missing traces were pretty similar. So how low can you go?
How low, as in like how much more missing data can we go? Yeah, there are studies that doing like 90% of missing data set, but the question is, do we trust that as well? So what we experimenting, we just use the numbers that we see in the real data set to train our data to mimic the real, what we use in the real world.
Gotcha. All right, thank you. If there's no other questions, we'll move on to the next speaker.